Good morning, everyone. Welcome to the webinar for Design Better Products with Simulation in Fusion 360, hosted by D3 Technologies. My name is Eric Schubert, and I'll be presenting today. If you happen to have any questions throughout the webinar, feel free to use the GoToWebinar and type those questions into the chat. I'll be happy to take a look at those and answer those as we get to the end of the presentation here. So let's kick things off. Again, my name is Eric Schubert with D3. I'm an implementation consultant. I currently deal a lot with AutoCAD, Inventor, and now Fusion 360, and specialize in the simulation area. So I deal with the simulation in Fusion, as well as simulation in Inventor and Nastran in CAD. So to start things out, I just want to go over the general topics that we'll talk about today in the webinar. We'll start with a general review of some of the simulation options that we have inside of Fusion 360, and then we'll go into a live demonstration of how to use some of those tools to help you design better tools or better parts inside of Fusion 360. And then when we're done, we'll wrap things up with some question and answer time. So the first things we'll go through are some of the different types of simulations in Fusion 360. And just to kind of go over those for anyone that might not be familiar, the first two types of simulations we have are going to be static simulations and dynamic simulations. And so the static simulations are generally non-moving. You have a constant loading situation, so something where you apply a load and just see how it reacts. Something, in this example, you've got like a bridge. Where you apply a load, weight of cars or something like that. Dynamic simulations tend to have moving components, whether that might be parts that pivot or slide. It could even be things like impact or drop testing. And they also include variable loading conditions, where maybe you ramp a load up or down, or you could even have things that cycle, vibration, or random loading, that sort of thing, where you want to see how things react with this variable loading condition. There's also linear versus nonlinear. Linear means specific materials that tend to act in a very linear fashion. If you imagine something like a spring, where the force increases in a linear fashion as you stretch or compress the spring a set distance. So if I take a spring and I expand that or stretch it twice as long, it ends up exerting twice as much force. But Fusion can also get into nonlinear simulation, where materials tend to act in a fashion where the reaction of that material changes and has a curving stress-strain curve. So things like rubbers, some plastics, even certain metals like cast iron, technically aren't linear materials, and so Fusion 360 can handle a lot of these nonlinear materials. We can also do thermal analyses. If we want to see how heat moves through a product or how something is cooled, we can apply different types of thermal loading conditions and see how that propagates through the material. So in this case, we can see a brake rotor that's being used, and as we apply friction and generate heat, how does that propagate through and end up stressing the material? So you can run just a thermal analysis to see how the heat propagates through your material, but you can also run a thermal stress analysis to see how does that heat then change the stresses inside the material. Event simulations are another type of simulation that we can do inside of Fusion 360. It's sort of a take on dynamic simulations, but in this case, we can see, again, how they collide, in this case, how the axe breaks through the material, but we can see how do components interact when we've got moving parts. So those event simulations tend to be time-based. So over some period of time, how do these parts interact? And then the last type of simulation is something that we're actually going to talk about today a bit, shape optimization. With shape optimization, we can apply some loading conditions to the material and see not just how it reacts, but we can see the different paths that the stress uses to propagate through the material. And based on that, we can choose how to remove some of that material from those components so that we can make our parts lighter, maybe even make them cheaper to produce, but they can still be strong enough in order to handle whatever load it is that we're planning on applying to those components. And so shape optimization tends to be coupled along with some of these stress analyses where I can run shape optimization, see where I need to put some supports within my parts and then remove excess material. But then we can also move from there over into the stress analysis to do a final run on our components to make sure that, sure enough, they will withstand whatever type of simulation it is that we're trying to run here. In this particular example, we're applying a torsion load to an arm for a suspension and seeing how that ends up reacting. And so those different types of simulations are all wrapped into Fusion 360. Some of them are inside of the Fusion 360 Ultimate version, the linear stress analysis, the thermal analysis, those are all built into the standard Fusion 360. The shape optimization, the dynamic analyses, the event simulations, those are all part of the Fusion 360 Ultimate version. And so depending on which version you have, that'll determine which simulation types you can run. So at this point, I just want to do a bit of hands-on demonstration and run through how would I take and bring a part into Fusion 360, run it through shape optimization, and then determine how I can lightweight my part and then put that through a stress analysis to see how it reacts. So I'm going to go ahead and hop over to Fusion 360 at this point. And so here is the component that we're going to be working with today. So this is an arm for a gripper of some sort. I imagine there's a second component to this where the gripper arm will clamp down onto something using this small clamping surface, and it pivots using pins inside of these holes. And I want to figure out how can I open up some of this material. Maybe if I'm having blanks made for me and then I'm going to machine it to complete everything, how can I construct this to make it the lightest gripper arm possible, but still make it strong enough to withstand the force? So I'm going to move over into our simulation environment inside of Fusion 360. And the first thing it'll do is ask me what type of study I want to run. And as I mentioned, I'm going to do shape optimization here as the first run. And it'll create a study here for my shape optimization. If you're familiar with finite element analysis, essentially the process is we apply loads and constraints to the model such that it's trying to replicate the actual real-world situation. So the first thing I'll do is apply a constraint to my model using these two holes to represent a pin being in there. So I'll select a pin type structural constraint here. The other thing I'll do is apply a load. And this could be done in a number of different ways, but I'm going to apply a load onto the gripping surface here and use 500 newtons as the applied pressure onto that surface. And so that'll represent our clamping pressure as we clamp down on our component. You'll also want to make sure that your materials are set correctly. It will use whatever material you set up inside of your model, but you can always go into the materials here and select something different. So if you need a different material, you can always override that and use anything from the library of materials inside of Fusion 360. And there are a large number of different materials in here. Okay. So as you run this, perhaps you'll try different materials. You can create multiple studies and select, maybe I want to see what happens with steel, but also with aluminum, and see if those two materials are different, and the aluminum material maybe being lighter could be a better option for me. Once I've applied my loads and constraints, I have to break down this problem, and I do that by converting this model into a mesh. And the mesh determines how many calculations are required in order to complete this entire simulation. The finer the mesh is, the more accurate my results will tend to be. And so ideally I would make this as fine as possible, but there's a diminishing point of returns where if I make it too small, it will just take forever to run, and it really doesn't tell me all that much more about my model. So I'm going to choose a specific mesh size because I happen to know the size of my part. So I'll break this down to a 3mm mesh and then tell it to generate that for me. And generally, generating the mesh should take just a short period of time. You can see here we've already got that broken down. It should recognize smaller features for you and reduce the mesh size there to help give you greater detail in those areas. But you do have some tools to reduce the mesh where you need it. You can also run these simulations on assemblies, and if you needed to do that, you can also generate contact between those assemblies and see how they'll interact with all the individual components. Now, once I've done that, I've set up my loads, my constraints, my materials. I also have to tell Fusion if there are certain areas of the model that I cannot remove material. And so where these holes happen to be, I need to make sure there's plenty of material there so that it supports those pins, it won't break as I apply the clamping pressure on my gripping arm. So we have an area where I can preserve a region of the model, and so I'll select this portion here and just tell it, you know what, I want to keep this intact. I'm going to do that with both of these holes to make sure that it doesn't remove material in those areas. I also want to make sure that I don't have a different amount of force on the top or the bottom, so I want to make sure the top and the bottom of this part are basically symmetrical. And so I'm going to apply some symmetry to my part to make sure that basically where the center line of this part is, the top and the bottom of that part end up being identical to each other. Okay. So I've gone through and set up my entire model. At this point, I would go ahead and tell it to solve. And when you solve, you can choose to solve either locally or on the cloud. Now, some of the simulation types require that you solve on the cloud. They tend to be some of the more complex simulation types. But some of the simpler ones you can solve locally. And here you can see I've got an option to solve either locally or on the cloud. Solving on the cloud does require cloud credits. I happen to have a bunch available, but when you purchase the software, you'll generally have a certain pool of cloud credits available to use, and you can always acquire more cloud credits as necessary. The advantage to running on the cloud tends to be complex simulations take less time to solve, and they don't take up the horsepower on your machine when you run the simulation. Versus if you run it locally, you save those cloud credits, but your computer is going to be working hard to solve that for however long that takes. So I would tell this to solve on the cloud. Now, for the sake of time, I've already gone ahead and told it to solve, and so I'll bring up the version that's already given me a solution here. And so you'll see how it broke this problem down and showed me various areas where I can remove material and still have a part that's strong enough. And when I ran this, you'll tell it what are you looking for your target? And generally it's going to be mass reduction. I told it to reduce my mass by about 40%. And so this is what it ended up coming up with. It generates this for me. And it tells me where the most critical paths that the load is being carried through the material. Now, based on this, I can take these results and promote this back over to the model. And if I hit promote, you'll see it pushes me back out to my model environment, but it gives me this purple or blue mesh here that shows me what I got from my shape optimization. I can then create a sketch and follow that to refine this down. So if I want, I can sketch here and just draw maybe a general shape that tells Fusion where I want to remove this material. And so I can extrude these sections out and clear that material and prep it for my final simulation run. Okay. Now, based on what I've gotten here, I've already given it a bit of thought, and I've cleared out some different areas of material here. Again, instead of making you watch me sketch, I've already created some sketches and extruded some holes here, leaving some structural areas behind to help support my part and also give it some stiffness as I apply the force. From here, I can go back into my simulation environment and create a new study to take this result and put it into static stress analysis. And I'll go through the same process as I did before. Well, I will apply my constraints, my loads. So I'll apply the pin constraints here once again. And I'll apply the load for the gripper clamping at 500 newtons on the end here. Okay. And again, I'll break down my mesh into a specific size. So again, I'll do 3 millimeters and tell it to generate that for me. And so once again, it breaks down my model into this mesh. Now again, the finer the mesh is, the better your results, the more accurate results should be. For the sake of time, I'm not breaking it down super fine, but I'm breaking it down fine enough that I know my results should be pretty accurate. And so then I go ahead and run that. And again, you have the option to solve on the cloud or locally. Now you'll notice I also have these previous simulation studies in here as well. So if I wanted to, I can actually create 2, 3, 4, 5, however many studies I want. And so I could clone those or just make additional ones and set all of them up so that I can run them all at the same time. So when I hit solve, I can just check as many of these studies as I want to run, push them all up to the cloud, and they'll solve simultaneously. So that's one more advantage to solving on the cloud versus locally. Locally, I can generally only run one simulation at a time, so I'd have to run them in order, versus on the cloud, I can run them all in parallel, which will save me some time. Now, once again, for the sake of this webinar, I've gone ahead and run this and gotten my simulation results already. And so with that, here you can see my stress results are showing me, based on what I created, where I have the most stress in my parts. It'll show you sort of an exaggerated version of the amount of this deflection based on the stress that I've applied. You can see how it's pushing this and stretching the material. And it also points out the minimum safety factor for my load. I can review the results using the information down in the lower right-hand corner here. I can switch over to viewing just total stress and see where I've got areas of greater stress. So down in these corners, I've got higher stress. You can also look at displacement and see how far does that move. sometimes it's not about the amount of stress. Sometimes you have plenty of stiffness or plenty of strength to withstand the amount of force, but it's about how much does the part move as I apply that force. So in this case, it's only about 0.15 millimeters. Okay, so not too much, but depending on what you're trying to solve for, that may or may not be above or below what you're trying to solve for. Okay. And so here's my safety factor again. I've got a safety factor about 1.4, which is pretty good. Any lower than that, and I'd probably be a little concerned that if someone clamped this down too hard, it might break or bend. But this particular result looks like it's pretty good. And so now I could insert this into my assembly and know that I've got a part that's strong enough to withstand what I'm trying to do with it. Okay. So again, just kind of a quick example here. We went through shape optimization in order to get this mesh result here that shows me where I can lighten up my parts, remove some of that material from my model, and then once I've gotten that put together, I can run it through the stress analysis and see how my parts will react. Okay. So again, it's just kind of a quick run through of the different simulations. We can do static stress, thermal analyses. We also have a couple ones that I didn't mention earlier. We've got modal, which is natural frequency analysis, and structural buckling. So if you're applying compression loads to your models. Some of these are, again, limited to the Fusion Ultimate version, but the items along the top here, the static stress, modal, and thermal analyses, those are all part of the basic Fusion, and so you'll have access to that if you've already got the software. So at that point, we'll go ahead and begin to wrap things up. Head back to my slides here. I appreciate you guys took a little bit of time out of your day, your morning, just to hop on here and see what Fusion 360 is all about, see what kind of analyses you can run in the simulation environment inside of Fusion 360. If you have any questions, feel free to contact us. You can head out to our website and check that out at b3tech.net. You can also email us. Our contact information is up there as well. We'll be happy to talk to you about Fusion 360. How can you utilize Fusion 360 in your workflow, in your environment, to help you produce better parts. If anybody has any questions, again, feel free to type those into the chat box. Otherwise, we'll go ahead and wrap things up here. And thank you very much for attending, and hope you have a great day. Complex assemblies in comparison to simulation mechanical. So Fusion 360 is designed to handle assemblies and individual part components. The assemblies for Fusion 360, I probably wouldn't do really large assemblies, but you should be able to get away with several parts. And generally for simulations, you'd probably try to break that down into slightly simpler, I guess, simulation models. Try to break that down into multiple problems versus trying to solve a really large assembly. But you would be able to import that and attempt to run it. And because of the cloud computing, you wouldn't have to type your computer for a long period of time. So it should still be able to handle some fairly good-sized assemblies. If you start getting into, hundreds of parts, you might start to think about breaking that problem down a little bit more. It's a great question.